Okay, everyone, we are officially live, and we're excited to have you all on our webinar. And this, just so that everyone's aware, is going to be a three-part series. So just keep an eye out for the other parts that we have coming out. It's going to be really awesome and exciting. I know that Wes has worked on some really great content that is extremely educational and also fun to learn. So we're excited to get started with this. Before we start, I just want to give a quick introduction. So my name is Ruthie Senanaika, and I work on the marketing and events side of things. So I will help coordinate these webinars. And I will pass it on to Corey, who will give us a quick introduction about Blueprint, the data science team at Blueprint, and then also introduce Wes, who will move it forward from there. But Corey is our Director of Data Science here at Blueprint. So Corey, take it away.
Yeah, thanks, Ruthie. Thanks everybody for joining, and looking forward to jumping into this. Before we do, just want to give a quick, who are we, right, at Blueprint? We're basically an all things data company, everything from traditional data warehousing and migrations to advanced analytics and data science. We've got handfuls of products and accelerators to help our clients get started quickly on these types of projects and realize that ROI sooner than later. Wes and I are here representing the data science practice specifically. We've got a wide team of data scientists from across the world, Europe, US, many different time zones working together all the time. Good stuff. We have a very broad experience in data science across many different industries, from retail, manufacturing, oil and gas, supply chain, many different areas, as well as some pretty significant depth in quite a few common machine learning and data science areas. Yeah, so today I want to hand it over to Wes to get us started. He's one of our principal data scientists on the team. Deep experience. He'll be sharing how to get started, a getting started guide on recommendation algorithms. What does it mean? Why do we care? And also demoing and sharing some code that will be available to anyone to check out after these webinars, just how to get your data science team started, hit the ground running on recommendations projects. So with that, I'll go mute and let Wes run the show here. Show us what you got, and yeah, let's see.
Hi, thanks, Corey. Thanks, Ruthie. So I'm Wes Cobb. I am a physicist by training. I was in academia for a few years, and then I went off and decided to write software and get into machine learning, and I've been doing that for the last 15 years. I've worked at several startup companies, a couple of oil and gas industries, and done some work for the government, even as far as satellites and sensors and things like that. And so now I've been at Blueprint for a couple of years now, and thank you for the opportunity to tell you about all of this. So let's go ahead and get started. First thing is, there we go. This is going to be an introduction to recommender systems, and it's the first of a three-part series of webinars. The first one is a sort of overview of the entire subject, and then basically I'm going to dive in a little more deeply into one of the types of recommender systems, an attribute similarity system. So what are recommender systems? There's something that every single one of us has dealt with and interacted with many times. It's probably unusual for you to even go a day without touching a recommender system somewhere. If you think about the interfaces on the internet for things like Amazon or Walmart or Costco or Best Buy or any of the big box stores, any of the big stores that have things like home improvement, Lowe's and Home Depot, things like that. Those are all recommender systems, those interfaces you have. They're intended to sit there and serve as a gateway for you to talk to the company and find out things about the products they have for sale. So what are they? They're essentially a software system that's intended to take the place of a personal contact that you really can't make because of being separated. So they take the place of a store clerk or a decorator, a designer, a movie critic, and whatever. They're designed to try to help you pick out products that you would like to buy based on information that you provide. They're not commercials, and they're not systems for delivering commercials. They're a thing for delivering product recommendations. A product recommendation is something that's based on a customer's expressed interest in something. They're based on data that other contributing users have given in the past and that people have determined from market research. And they're based on things that come up when you're doing your interactions with the user interface. Product commercials are very different. They're based on a seller's interest in selling a particular kind of product, and they're while they can be unbiased, they usually aren't. They're usually deliberately intended to make you buy a particular product rather than what you might really want or what would be the best match for what you want. So this business about where do they come into play? Well, recommender systems are things that help you choose any of these sorts of things, any sorts of items where there are many, many choices to make, and they're designed to help you kind of pick the needle out of the haystack. So physical items, abstract items, virtual items. Ultimately, they're about pulling one piece of information out of a whole bunch of pieces that are available. You use lots and lots of data to do this. And that's one of the big differences between this and a commercial sort of advertising sort of situation. In this particular case, there are two main families of data that we're interested in right now. That's what's called structural data, and that's what's called targeting data. Structural data is data that users have passively contributed in the past or that you've gotten through surveys and measurements about your user base. Targeting data is data that a user whom you're currently talking to is actually contributing on the fact. It can also be things like interactive data from the current session. To dive a little bit deeper into that, behavioral structural data is content of the sort that gives you information about what products customers have purchased, what products other customers who purchased these same sorts of things have bought previously as well. That way you can try to correlate what one user is looking at versus what other users have bought in the past. What types of actions and searches and queries did users do prior to buying this product? So were there particular strings that were used? Were there particular other customers in different contexts that came here from other websites? That's a possibility. Personalization data. These are things about your user, about your customer. Where does the customer live? Where is the customer right now? That's actually not necessarily the same thing, right? You might be having someone contact your website from Starbucks rather than at home. What's the customer's likely political orientation and socioeconomic status? All sorts of things that are kind of not PC to think about, but we do need to know those things when we're trying to target things that we recommend. This information is generally something you can pull out of the information about the user. You can tell what kind of computer the user is using. You can tell what parts of the country the user is calling from by looking at where the IP address that's available in the internet connection is coming from. You can find out all sorts of things like that. So that turns out to be useful in kind of characterizing your user. Data about satisfaction. People do surveys. They go back and they look at products that they've sold. They ask users about what they think about the quality or the appearance or the workmanship of it. They'll sometimes ask for text reviews. The text reviews can be solicited, they can be unsolicited. Unsolicited reviews tend to be outlier cases, meaning they're not normal reviews. They're either something where the person loves the product or the person hates the product. So you have to be very careful when you see those because you worry about them. Targeting data. Okay, so once you've got a user talking to your recommender system, the user makes various choices when talking to the system. There's selections you make, there are buttons you click, you go and browse to certain things, you supply search information. That information is kept and used to build a profile of the current session that is going on. And then possibly text or query strings from that session as well are kept and used as information to try to help refine the choices. Structurally, a recommender system has two main components. There's a user interface, and then there's a recommender engine that kind of sits in the background that you don't really see directly if you're the user talking to it. But that recommender engine in the background has several pieces to it. There's some control logic for making the program run properly and talk to the data sources, in particular the structural data that you were looking at. And there's actually a machine learning model, and we're going to talk about that in a minute, that basically takes that information and with it uses the targeting information that's been gathered during this session from the user interface, and then uses that plus the structural data and basically makes a refined prediction about what you might want to buy. Now, when I talked about machine learning model there, what I'm thinking of doing is what we do is we take an algorithm that is specifically designed to be able to learn from information it's given and learn to predict a particular output. So the idea is take a bunch of data, lots and lots of that behavioral, personalization, and satisfaction data, put that together, and use that to try to predict what the satisfaction result would be. You take a good chunk of that data, maybe 2/3 or 3/4 of it, train a model based on that, and then test the model against the remaining fragment of data and see how well it does. And you keep refining it, tweaking numbers and changing the details of the model until you get something that's better, until it gives the best result you possibly can. So a machine learning model. Machine learning is one of these weird little things that you hear about in the press all the time now. And it's interesting because historically it was one of the two main branches of artificial intelligence. There was this branch called expert systems and there was a branch called machine learning. And expert systems were based on rules. Basically, you took a computer algorithm that you constructed by basically codifying a bunch of questions and answers to questions. And if you think about what a doctor might do when trying to diagnose an illness, gee, does the person have a fever? Does the person have spots all over her arm? Is the person perspiring copiously? Is the person unhappy or lethargic? Those sorts of questions, if you can give it sort of a yes or a no answer, that's a perfect sort of setup for an expert system to be. And it's the nice thing about expert systems is they're very, very fast and accurate if you give it questions that it knows how to answer. Unfortunately, it doesn't work at all for cases where you haven't anticipated what the questions might be. Now, the other approach to things is what was called machine learning. And in machine learning, you take a computer algorithm, you keep iteratively exposing it to a bunch of data and try to get the algorithm to try to be able to learn to estimate what the data means and what the next answer, what the data will predict as a result. They turn out to be very fast and accurate. Maybe not as accurate always as an expert system is, but the difference is they even work with somewhat reduced accuracy when the target data doesn't look anything like what you were training it on. That's a really good thing. The one drawback is it takes a lot of effort to train such a thing and to train a machine learning model. Now, what's happened is in the last 20 years, we've gotten much better computers with things called GPUs, which are basically number crunching units that exist that help do training of algorithms much faster. And as a result, the natural split up between expert systems and machine learning got all bent out of shape. Machine learning basically ate the world. And so now you have all of these different branches of machine learning, and most of the work in artificial intelligence now happens in that sandbox, part of the sandbox. And it's interesting that you've got these areas: deep learning, computer vision, time series analysis, natural language processing. Recommender systems are interesting because they actually, although they're heavily built on machine learning algorithms, they also touch the use case of expert systems. Give me some specific questions and answers, and can I then predict what you really want? And can I give you a recommendation for it? So that's where we are right now. We're on something that's sort of straddling that line between the two. Now, it turns out that if you go and look at recommender systems in the broad from 50,000 feet, like an airplane, it turns out there are four main types of recommender systems. They're what are called attribute similarity systems. Those are systems that take a bunch of properties that you supply, the user or the customer supplies about what he or she's looking for, and then tries to make recommendations. There are collaborative filtering systems. Those are systems where you take information about lots and lots of customers over time who've looked for things similar to what you're looking for and focus on trying to recommend things that those other customers liked an awful lot. There are clustering-based systems where you try to identify the properties of your customer and the properties of the kind of products that the customer likes, combine those together, and then come up with a way of recommending that, gee, customers in this group tend to like products in this group, and you basically kind of try to guide the selections that way. And then there are hybrid systems, which sort of use combinations of all of those. If you actually put together sort of a tree that describes what these things look like, you end up with basically three main branches to the tree. And in each of these cases, things can be generic or personalized. That is to say, you can have something that makes heavy use of the data that you infer about the person based on the current session the person's talking to you from, or properties you can infer about the person. Or you can basically try to do things that are completely general instead, that don't do that just use things that are true of all people. And you can have what are called static or dynamic versions of the systems. You can have things where the data that you're working with stays the same. You train it once when you build your models in the first place, and then nothing changes afterwards. Or you can have it be dynamic. That is to say, as people use the system, you can keep updating the data dynamically based on their recommendations, their reviews, their assessments of the suggestions that you made. And so that's a dynamically adjusted system. So far, I've kind of talked about just some of the basic overview of recommender systems. What I'd like to do now is shift and begin to talk about an attribute similarity system today. And that's going to be basically the one that we talk about in this webinar. In subsequent webinars, we will focus more heavily on collaborative filtering systems. And in the third webinar, we'll focus on cluster-based recommender systems. So without further ado, meet the beer finder. Okay, so what we're going to build is an attribute similarity recommender. And Beer Finder is a very simple system that does that. What it's going to do is ask a customer to describe what he or she likes in a beer. And then what the system's going to do is search through a big list of beers that we have reviews for and basically try to pick something that has properties in the reviews that basically line up well with what the person said. The example's a little bit frivolous, I know, but it helps to show the process that we're going through. And what we're doing here actually is more general than it might appear. In many, many cases, users are asked questions about what they want or what they're looking for. And what this provides is a way of looking at what the user has asked for and then refining that and searching through information you have and finding a good match. So that's something we do a lot. In terms of that hierarchy, that taxonomy we showed a minute ago, what we're looking at is really a system like this. It's a recommender system. It's attribute similarity based. It's personalized because we're going to use personal information, and it actually is a static system. It's not going to change with time. The data that we're going to be working with, it comes from a couple of data sets on the internet. One of the cool things about being a data scientist is that the internet gives you a way to get at lots and lots of different sources of data. And if you go hunting around, you wouldn't believe it, but you can find data on almost everything. And beers is one thing that's seems to be a fairly popular thing to talk about online. There are two good data sets. One's called Rate Beers and one's called The Beer Advocate. They're actually whole websites devoted to this sort of thing. And those two data sets, they're very similar in format. And between them, they have about 4.5 million contributed ratings for beers. And it covers more than 129,000 different beers from scattered all across the world. Every one of the records that are in this data set has the name of the beer and the brewer, the style of the beer. There's a code name for the reviewer, so you don't have to know exactly who the person was. You can just sort of kind of sweep that under the rug and not pay attention to it if you want. There are numerical scores talking about what the appearance of the beer is, what its aroma is like, what its palate is, that is to say, how it feels in your mouth when you're drinking it, if you pay attention to such things, what it tastes like, and then sort of an overall ranking of just, gee, if you add all that together, what do I think? And then basically each person was asked to contribute a text review. And so people were supposed to write a sentence or two or a small paragraph describing what they think about the particular beer. So that's what we're starting with. And what we're going to do from that is we want to create this personalized recommender system. So we're going to also be wanting to gather information from the users and somehow connect it to this data set. Well, we know already that what we think we want to do is basically have the user contribute a small blob of text saying what they want, what they think they like. And then we're going to basically try to match that up with the data sets that we've got. The way we'll do this is to ask them to describe in their own words what we want the properties to be. And then we'll actually let them go ahead and to try to help in the refining process, we'll let them pick out whether they would like to focus on aroma or appearance or palate or taste or that sort of thing, just to make it a little bit finer tuned. Sorry. To prepare the data, we're going to build a little data pipeline. This is one of the things you always go through when you're doing machine learning stuff online. And what we're going to do is we're going to basically make a data pipeline that takes those two data sets, and it's going to combine the two data sets together and make sure they're in the same format and are compatible in that way. And then we're going to collate the results by beers. Now, what you've got is we've got 4.5 million rankings of 130,000 beers. So that probably tells you that there's something like 35 or 40 contributed ratings on average per beer, if you go through the whole list of beers. And so that means there are a lot of people who contributed ideas about what they think about a particular beer. So what we'd like to do is basically average the rankings that people gave across the appearance and the aroma and the palate and the taste and so on. And then we're going to add together and aggregate, pile up all the text from all those things and make the equivalent of like a small PDF summarizing the properties of the beer that people have talked about. In addition to that, because some of the beers are much more popular and people pay much more attention to them than others, you may have a beer called Joe's Beer from some obscure place in rural Idaho that has one review contributed, whereas you might also have Heineken that has 30,000 reviews contributed. So what you'd like to do is have some way of kind of noticing which beers seem to have a bigger market presence or a bigger popularity or a bigger significance to the community that's been contributing the ratings. And so we constructed an artificial column that we're going to add to the data set called gravitas. And basically that's from Latin for weight or impact. And that's the basic idea is that number is going to sort of characterizes how much data was in there for that particular beer. So a big number means that there was a lot of data. A small number means there wasn't so very much. And then we're also going to do a filtering after all of that. And if we've got very, very few entries, very few records for a particular beer, we probably will not use that beer in our table. And if we've got insanely large amounts of records like Heineken with 30,000 reviews, we'll probably only keep the first few thousand rows of text rather than keeping several million rows of text. So the result is we'll keep things to it'll winnow down the size of the data set a bit. We'll go from actually about 130,000 beers down to about 30,000 beers. Now, mind you, 30,000 beers is still an awful lot of beers to pick from. So how do we start doing that? Well, one of the things that we're going to talk about is natural language processing. We're going to be wanting to look at this text that the users are going to be writing. So we have to go to a branch of artificial intelligence that focuses on dealing with text and language in general. Natural language processing is that branch of AI that focuses on working with human languages. It does all sorts of things. It can analyze and parse text and tell you this is a noun, this is a verb, and so on. It can actually be used to write prose and poetry, which sounds crazy, but you can actually do it. You can actually have create an algorithm that will learn the style and content approach that various authors use. You can have an algorithm, for example, learn to write things in the style of Lewis Carroll, Jabberwocky, and so on. You can try to understand what the text means, what the content really means there, not just repeat the words and so on. You can prepare translations between different languages, which is, of course, you'd have to have several of those things that you've just mentioned to be able to do that. Two of the areas in natural language processing that we're going to focus on is an area called, in a particular thing, it's called Ngrams and something called similarity. Ngrams are very short groups of semantically connected words. We'll talk about that in a minute. And similarity is a way of estimating how similar or different a couple of strings are. In our particular case, we're actually going to be comparing these short groups of connected words, the Ngrams, and so we're going to be looking at the similarity between Ngrams. It's a very active field of research, and there are hundreds and hundreds of algorithms and packages that are out there that people can work with to build things. And we're going to be using a couple of the more prominent ones in a moment. Just to dig a little bit deeper on what an Ngram is, Ngrams are short sequences of words that occur frequently and are known to have some sort of semantic connection. If you think about pairs of words that you see a lot of times in language, blue sky, oppressive heat, cherry red, those are examples of two-word Ngrams, sometimes called bigrams or digrams. And then you've got like three-word Ngrams, 10-gallon hat, country western bar, French fried potatoes, and so on. And that's trigrams. And there are 4-word and 5-word examples as well. You have relatively few when you start getting out to like beyond about 5. There are not too many things that have 6 or 7 words that are always tied together. But the thing is, if you take a paragraph of text, search through it, and find the Ngrams in it, you'll end up with a very short list of, say you've got a page of text, you might end up with a list of about 10 or 12 Ngrams that turn out to be key semantically connected elements in that text, in that page of text that you have. In a way, it's a way of getting a sort of semantic summary of things that are being talked about. So comparing the list of Ngrams from one passage of text and another gives you a way of estimating how similar the two pieces of text are, or what the texts are talking about are to each other. That's where we're going with this. Now, there's some tools for doing this, for finding Ngrams. There is a package called Spacey, which is this really high-end language toolkit that has been constructed that's by some really smart folks in Europe. It has more than 20 human natural languages in it right now. And there are actually another 60 languages in work, but it has things like French and Spanish and German and Italian and so on. And in all these cases, what they've done is they've looked at literally every meaningful example that would ever come to mind to you of things that are being used in the language these days on the internet. They'll go look at encyclopedias, they'll look at articles, or look at news stories. And it takes all of those and studies the entire corpus of all of that content, and then builds a model for what contemporary usage in that language looks like. And then it takes that and decomposes it into these pieces we're talking about. And in particular, there is a package called Textacy that uses that Spacey language model that gets built and is designed to extract useful Ngrams from that. And so we're going to be taking Spacey and Textacy and using those with the content that's going to be contributed to us from the user interface that we're going to build to basically get lists of Ngrams that summarize what the user wants to talk about. To do that, we're going to build an extra little block to stick on the end of that data processing pipeline that we had. We're going to call this little block the Ngrams list extractor. And what it's going to do is going to take a paragraph of text. It's going to clean it up. and then it's going to run it through this spacey-based text-to-see Ngrams feature, and it's going to extract out a list of records that are basically these Ngrams. And then we'll take that and use it to build our system. Now, with our initial data set, we're going to process all of that initial data that we had, run it through this Ngrams list extractor, and we're going to get a modified version of the initial data set that has all the initial data, but then beyond that, it's going to have that gravitas feature that we talked about, and it's going to have these lists of Ngrams, and we're going to call that our recommender data set. So what that's going to have, just to reiterate, it's going to have the beer, the brewer, the style of the beer. It's going to have the aroma, the overall score, the text, the appearance, the palate, and the taste. It'll have that gravitas score, that rough indicator of market presence, and it's going to have that list of key combinations of words. If we combine all of that together, we have to have a way also to compare that list of Ngrams that we end up with here in the recommender data set with those lists of Ngrams that are going to be contributed by the users as they use our user interface and talk to our recommender system. To do that, you have to have a way of measuring how similar particular strings are. There are a bunch of different algorithms for doing that. There are two principal kinds that are used for strings. There are what are called constructive algorithms, and those are algorithms that basically focus on the structure of the string itself. String is just a sequence of letters, right? And a constructive algorithm basically looks at comparing one sequence of letters with another. And it may characterize that by how many of the letters are exactly the same in exactly the same location. It may characterize it by how many letters you have to move in one or change in one to get to reproduce the other string. You have to handle special cases where the strings are different lengths and so on, but that's the general approach that's used. There's some algorithms in this family that people talk about all the time and use regularly: Jacquard, Sorensen, Hamming. These are typical algorithms that you'll hear mentioned if you go digging around in the literature on this. Those are the things that people often use there. In our particular case, because we're focusing on building these lists of semantically connected words, we're going to focus instead on what are called semantic algorithms. And those are actually algorithms that think of a string as being decomposed into words. So think of a sentence, and rather than talking about all of the individual letters and the spaces and punctuation marks in a sentence, we're going to talk about a list of the words in the sentence. And we're going to worry about which words come in what order and which words come first and which words are missing or not missing. And so we'll be comparing sequences of things. So pretty little blue dress versus pretty little dress versus pretty blue dress versus little blue dress versus big blue dress, and so on. Those are different combinations or sequences of words, and we would be comparing them using these algorithms. And the one that we're going to focus on is the one called partial token sort ratio. And I'm not going to go into that for detail because it's nitty gritty and it's really not necessary for the scope of this discussion. But what it does basically is look to see how similar the sequence of words are and how many of the words in the sequence are correctly in the same order that the other one is. And that's basically what it does. And then it gives you a score based on that. And that's all you really need to know. So if we put that together, our recommender engine box that we had way back near the start of the deck is going to actually look like this on the inside. There's a user interface that passes the user preferences in plain text into that Ngrams list extractor. And then we go down, then we go down and we basically loop through all of the recommendations and lists of Ngrams that are associated with the beers in the recommender data set and compare each of them as we go through it. And then we make a sorted list and we rank it and look at the answers. And then we say, okay, I'll take that. And I'll also take what the user has given me as additional guidance about the appearance, the taste, the aroma, and so on of the beer. And then we'll use that to come up with a final list of recommendations that we give back. So that's the approach we're taking. That's what we're going to build. And actually what I was going to do now, we actually went and built that. And I'm going to jump out here to another screen in just a moment, assuming I can do this without spazzing out. There we go. Okay, so we built this in Databricks actually, which is a development environment that lives in Azure. It's some other places as well. But basically, we implemented the recommender system, and this code is there, and you can actually go look at it in the Azure Databricks. We'll post a link to this afterwards associated with this talk. But the code for doing this is for setting up the environment is there. There are a bunch of utility functions. I'm not going to actually ask anyone to look at this right now. I'm just going to scroll through it so you can see that there is code there that shows you how to do all of these things. We actually retrieve the data set from the internet, from a source. We pull it in, we clean it up. This is what it sort of what a little sample of the data looks like when you come first through it. So you've got this listing of things, you've got this listing here, and it's got a description of the beer. This is the review text. This is, oh, it has a brown color and it's a very light colored, it's very light foam, it's nice and tasty and so on. It's got various numerical rankings for the various parts as we talked about. It goes on like this for hundreds of thousands, well, actually millions of rows, but we're just printing the first 10. We clean it up a bit, and there's code here for doing all of that and setting it up to what we want. And we end up with we added that gravitas thing that we calculated. And then we go and extract Ngrams. And that's what this next blob of code does. And let me scroll down a little further. We extract Ngrams and we actually put it into a final form. And then if you look here closely, and this next to the last column that says Ngrams, you'll see that there's a list here. And this is a list that has word combinations. It's milk chocolate colored. Oh, it has a malty aroma. It's got a white head. It's small, small bubbles and so on. That's the idea. And then we basically have basically a control program that ties all of those pieces together. And then we pass that into a very simple user interface at the end. And the user interface looks like this. And it's nothing fancy. It's just a little simple gadget, but you can basically go through here and I'm show you what it looks like. If you try to run it without giving it information, it tells you, no, that's bad. All right, so let's give it, well, this is what I had typed in before. So, I mean, if we do taste and aroma, and so I'm saying I care about taste and aroma, but I really want a hoppy beer that's got a dark amber color and a nice head of foam, and it's kind of fruity with a hint of cherries and chocolate, which sounds wildly pretentious, but you actually can taste some of these things if you're a beer snob, just the way a wine snob can taste a bunch of things also. So anyway, if you put that in here and let it sit for a little bit, and it's not very fast. This was really intended simply as a demonstration program, so it takes about 10 seconds to do this, to find this calculation. It'll run in a moment, and we'll get an answer out. But there we go. And so what it comes back with is a list of beers that it thinks are the best matches to what we have. And if you look through here, you'll see there are things you may, you've probably heard of Sam Adams Millennium. There's some beers in here that you may have heard from if you're from one part of the country or another and may not have ever heard from otherwise. I've never heard of AleSmith Vanilla and Coconut Speedway Stout, for example, but someone might have heard of it. The point is you can tell this thing basically to go and do that. If you change it and say, oh, I'd really rather pay more attention to the appearance of the beer, and I don't really care about that it has a nice amber color. Maybe I want it to be, let's see, nice head of foam, fruity. Let's say we want it to have a hint of orange chased. Or say we want it to be orange flavor, and we want it to be a light amber color. And if we do that, it'll probably take a few seconds as well. You'll get a very different recommendation, which is kind of cool because that's what it's supposed to be doing. And so if you look here, and this is almost an entirely different group of beers, which is not surprising. You've asked for different things. So that's the way it works. And it's a very simple application. No one was trying to claim it was going to be some amazing thing. But the point is, it's kind of fun to do. And that gives you a simple sense of how it works, though. Let me go ahead and bring this back to full foreground again for a moment. There we go. Okay, so we created a basic recommender system that generates customer recommendations using text strings that the user supplies. The intention here was to basically show you how you might go about building one of the systems. It's a very simple user interface. We could make something much fancier than this if we wanted to, and it's kind of slow. And so what we would do if we were going to commercialize something like this is we'd add a much nicer user interface that was kind of sexy. And then we'd also work on improving the speed so that it was basically instantaneous like that to get an answer back. But that should give you a feeling at least of what it's like to build one of these systems. All right, so to summarize kind of what we've been through today, we presented an overview of recommender systems and talked about the basic idea behind them, how they rely on data, how they're not giving advertisements, they're giving recommendations. We talked about different kinds of recommender systems, how recommender systems sort of tie into artificial intelligence, talked about a little taxonomy of them. And then we described in some detail how an attribute similarity system could be built. We talked about preparing the data, how we would go about implementing that. We talked about the system architecture a bit. We made it when then we created and gave a demo of the system. And that's where we are. Any questions?
Awesome. Thank you so much, Wes. That was really, really great information. If you have any questions at the moment, feel free to add them into our Q&A section. You can add them with your name, or you can add them anonymously. If you don't want to share your name, that's totally up to you. Actually, looks like we had one come through, and I'll read this out for you, Wes. It says, how valuable are these types of systems for a growing company that is not in the beer industry?
Of course. So yes, the beer example, as I was saying earlier, it was kind of frivolous, I know. This particular example is actually quite good. If you have any sort of situation where you would ask a user to tell you something about what she thinks about your product or what she's looking for on your website or from your company or from your product pool, you can use the approach that we mentioned right here to actually tie that to your products, as long as you have descriptions for your products. So as long as you've got a text passage describing all of your different products, you can match what the user is, what she's supplied in her text description to what your text description of your product is, and get a very good answer that way. We did more than that, of course. We also had numerical rankings for what users thought about the particular aspects of the product. You could add a very large list of aspects that didn't have anything to do with beer. You know, you could talk about the color and the strength and the weight and the durability and the materials that a product was built from. You can talk about other characteristics of the product. If it's something more abstract, like movies or a service or a piece of software or something, you can talk about a lot of other aspects of the product as well. But I think it's actually much more useful than it might at first appear. And so, anyway,
I'll just chime in here a little on that one too. Just kind of ideas of numbers on these two, right? There's papers on archive and things. I think a couple of years ago they did a survey on recommender systems that have actually been implemented in industry, real ones, and what kind of ROI were people seeing. Top of my head, some numbers I remember. I know Amazon quoted 35% additional revenue specifically from recommendation algorithms, which is enormous. That's not what I would expect everywhere. I've seen personally in a couple retail settings around 10% additional revenue driven specifically from recommendation engines. And again, what we're seeing here, right, what Wes was demoing today is the intro to the topic. Here's a way you can do it, how to get started. But obviously, when you implement something like this, a lot of the value you're going to see comes from fine-tuning these things specific to your industry,
Absolutely.
to your customers, right? And this is why it's so data-driven and why it's so, it's very much a machine learning data science project. But for the general case, I've got an online portal selling some stuff and what should I expect here? I think getting started, you would typically expect between 1% and 5%. I think around 2 or 3% additional revenue is the expectation. And that's just revenue, right? So a percent-based increase in revenue is a really big deal for most people, but then there's also an enormous amount of control over the user experience that you generate by having these algorithms. You can guide people to where you want them to go next. You greatly increase things like click-through rates, the customer journey, conversion rates. There's a ton more value in a recommendation system than just the revenue it generates, but the revenue is pretty substantial for algorithms like this as well. Cool one. That's a reason we care about these. Yeah.
Thanks for that, Corey. We actually had another question come in that says, I've read about the role of stated preferences versus revealed preferences to drive recommendation or recommender engines. Are you familiar, and can you expand on how you gain insights when stated and revealed don't match for a person?
Yes and no, but yes. Even the system that we have right here, the simple little system, if you noticed, if the person asks says a bunch of preferences in the text passage that we had, the text blob that we provided, back up here, if I can send that back. If you look at what I've typed right here in this particular window, this might be what I say that I care about, except that if I clicked different things in that window, in my choices for what to prioritize, that should tell you that in fact they don't match very well, and in fact there are preferences that I have that I'm not really revealing. I'm just, even though when I asked for what I thought I liked in a beer, I didn't say the same thing. It's much more subtle in the case where it's something that's a covert or a hidden preference. If you have enough data about the user, you can do a great deal more. If we were retaining a history here rather than just doing a static system, we could do much more than this. With a dynamically updated system where we kept a record for each user who had interacted with the system, then what we could do is understand what the user's real underlying preferences are based on selections that she has made in the past. It's rather difficult to do that with a system that doesn't retain state at all, the way this one that I implemented here was done. You can do it. It's something that shows up in the collaborative filtering case a lot more as well. And that's something that will be talked about actually in the next webinar to some extent. So I'm sorry that may not be the answer you want to hear, but that's about where we are with this.
Thanks for that. Go ahead, Corey.
Add a little more to that. It's a cool topic, right? It kind of comes, you have two different data sources and you kind of, it's almost like what do you trust more? What they tell me they like or what they have been purchasing, right? So it's as simple things like even with the beer finder here, right? So if I type, I really want a very hoppy beer. I'm not a beer snob, so I don't know all these words. So I'm going to say hoppy beer, right? Maybe that's what I search for. And maybe the recommendation algorithm presents to me some really good matches based on that. And I click through them and I'm clicking around and I don't want to purchase any of those beers. I end up buying a beer that is described by my data as not very hoppy, right? Well, now our system is going to record this. My purchase history will remember that Corey doesn't purchase beers that are hoppy. He looks at beers that are hoppy, but he doesn't purchase them. And those are two different things, right? Sometimes you want people to see the products that they're asking for, but you need to keep in mind what they're likely to buy. What's the conversion how do we lead them to that conversion, right? So yeah, both valuable data sources to improve the customer experience, but just two parts of knowing your customer, right? Two sides of the same coin.
Thanks for that insight, Corey. Any other questions that we have before we wrap it up? Okay, well, thank you everyone so much for joining again, and special thanks to Wes for putting this all together, and for Corey as well. We are really excited to get this recording up, so we will be posting this on our social media as well as our website. So keep an eye out for that. If you're not following us already, we're on essentially all the platforms. So go follow us. That's where we will be posting our next webinar. This is the part 2 of this series that will be coming up soon. So keep an eye out for that. If you have any questions, feel free to connect with us on LinkedIn. You can connect with myself, Ruthie Senanaika, or Corey or Wes, whoever you'd like to connect with. You can also email info@bpcs.com and we will get back to you right away. But thank you all so much for joining, and we hope you have a great rest of your day.